All right, we have 4.3 multiplying matrices, day 2, to get to the rest of this. All right, so today then we're going to be working on the third part here, representing a system of equations using a matrix equation, and also doing some more with multiplying two matrices. Okay, so we're going to talk about a different type of matrices today. So every matrix has an additive identity, okay, or O, we call that. But only a square matrix, or matrices, have a multiplicative identity matrix, which is represented with an I. The cool thing about this is if we take any matrix and multiply it by its identity matrix, it's equal, all right, a typo there, to the identity matrix times that matrix A, which also equals matrix A, either way. Okay, so the identity matrix, just think of like the multiplicative identity. We multiply any number times 1, and we get the number. That's the same thing here, right? A times 1 equals A. Or if we do 1 times A, it equals A. The order doesn't matter. And here, the order doesn't matter either. We could do A, matrix A times the identity matrix, or the identity matrix times matrix A, and we're still going to get matrix A. All right, so a multiplicative identity matrix is a square matrix with 1 as each element on the main diagonal. So if we look at this example, see this main diagonal starts from left to right, or starts at the top left and goes down across to the right. So every element there is 1, and every 0 is every other element in any square matrix. So that's what this one is saying too. It doesn't matter how big the square is. The top left is always 1, and then that's called the main diagonal, is always a 1. Everything else in there is a 0 for an identity matrix. Okay, so now that we've got that down, let's actually put it into practice with example 4. So it says, given matrix A, 3, -1, 8, 12, find the identity matrix times A and A times the identity matrix I. Okay, so first of all, since this is a square matrix, it's a 2 by 2, okay, the identity matrix, so I would equal 1, 0, and then 0, 1. So we can see right here is our main diagonal. It's got 1s in it. Everything else is a 0. Okay, I'm going to take that back out of there. I just wanted to highlight it to make you so you could see it. So then we're going to multiply these. So I'm going to take I, 1, 0, 0, 1, and I'm going to multiply it by A, 3, -1, 8, 12. Okay, so we're doing a 2 by 2 matrix times a 2 by 2 matrix. So we check those numbers, they're the same, and the outside numbers are our result, right? We're going to have a 2 by 2 matrix for a result. So let's do the work here. So remember our rules to multiply. We're going to take 1 times 3 plus 0 times 8. Then we're going to keep our first row, multiply it by the second column. So 1 times -1 plus 0 times 12. And then we're going to move down to the second row. So 0 times 3 plus 1 times 8. And then 0, we're going to move over to the next column. So 0 times -1 plus 1 times 12. We put some equal sign here, and we'll put some equal sign here. So 1 times 3 is 3 plus 0. So this number is going to be 3. -1 times 1 is -1 plus 0 times 12 is 0. So that's going to be -1. 0 times 3 is 0. 1 times 8 is 8. So this is 8. 0 times -1 is 0. Plus 1 times 12 is 12. So this location is going to be 12. And there is our matrix. Now, we can check this. It said it should equal A. Well, it does. 3, -1, 3, -1. 8, 12, 8, 12. Okay, so it does equal A again. So this one, A times I, we're doing the same thing, but we're multiplying A first. Okay, so we've got the 3, negative 1, 8, 12 times 1, 0, 0, 1. It's still a 2 by 2 times a 2 by 2. So we have 2 in the middle for both of them, and so our answer is going to be a 2 by 2. All right, so we're going to do 3 times 1 plus negative 1 times 0. I'm going to move over to a column. So 3 times 0 plus negative 1 times 1. Move down to the second row. Start over. 8 times 1 plus 12 times 0. 8 times 0 plus 12 times 1. Okay, so 3 times 1 is 3 plus 0. So this gives me a 3. 3 times 0 is 0 plus negative 1. So that gives me negative 1 here. 8 times 1 is 8 plus 12 times 0 is 0. So it gives me an 8 there. 8 times 0 is 0 plus 12 times 1 is 12. So that gives me a 12 here, which again is identical to what we started with in matrix A. Okay, so that identity matrix, you can multiply it, but you don't, like you're learning that this is the thing. If you multiply by an identity matrix, you're still going to get the matrix out. So you wouldn't even have to show all the work unless it said show the work, right? Okay, now let's get into that last part, this matrix solving a system or representing a system of equations using a matrix. All right, so matrix multiplication allows a system of equations to be written as a matrix equation, which is going to be pretty helpful, okay, as we get further and further in. So we have 3 equations in this system, okay? Notice all 3 of them have an x, a y, and a z in this case. And we have them all in order, right? X, Y, Z, X, Y, Z, X, Y, Z. They won't always be written like that for you, like when we're solving them, but we're going to start out this way. Okay, so if you notice, it says these 3 equations can be written as this matrix equation. All right, so what we're looking at here, okay, is that we're taking this first part right here, we're taking the coefficients out of here, the numbers, right? The coefficient is the number that's with the variable. So the 3, a positive 1, a negative 4. We're taking those out and putting them over here in the matrix for each of these. So we're pulling out the coefficients. Okay. And we're putting them into this matrix, which is why it's called a coefficient matrix. Okay, so this first part is called a coefficient matrix. Then our x, y, and z, they were all in the same order, and they need to be, because we're bringing those in here, and we're putting them here in a column, x, y, and z. Okay. This is called x. It's our unknown. When we've solved this before, we've had a matrix equation with an x in there. We're solving for that matrix or solving for those values. And the last one is what's on the other side of the equal sign. These are all the constants, right? The answers. Those are the numbers that they're equal to. And we're putting the constants in this last matrix, which is called a constant matrix. So if we look at this definition, this system is written as the matrix equation AX equals C, where A is the coefficient matrix. So this one right here is A. This one right here is X. We've already talked about that, equals. Okay, and C is the constant matrix. So these are the constants. Okay. So AX equals C. Okay, so we're taking the coefficients times the matrix with the variables in it equals the constants that we've got. So pretty simple to pull out. And if you know how to solve a matrix, they're a lot simpler to solve than just a system of equations. All right, so step 5, we're just going to write the system as matrix equation. That's it, first of all. Okay, so first thing we need to check, we've got x and y. They're in order, right? They're both, the x's line up, the y's line up, so we're good. Okay, so we're going to take, we have 2 equations, so it's going to be a 2, and we have 2 variables, so it's going to be a 2 by 2. All right, our coefficients here are 3 and positive 4. Our coefficients here are 2 and negative 2. So that's my A. Then I need my X matrix, so it's X, Y. Okay, and this you may be thinking, but like all my x's aren't in this row. They don't have to be, because remember when we multiply, we take these numbers and we multiply them this way. We're going to do 3 times x and 4 times y, right? Okay, this is going to equal our constants. So it's going to equal 7 and 4. All right, that's it for example 5. We just had to write it as a matrix equation. That's all. Okay, let's do B. B is going to require a little bit more work. This one has a y and an x, a y, and a z. This one has a y and a z. So we're going to have to do some work to problems when they show up like this to get them in order. All right, but remember, we need our constants on the right side because we need our coefficients, our variables, and our constants. So let's rewrite this. We're going to subtract 2x from both sides. So we're going to have negative 2x plus y equals 5 for that one. This one is good, x, y, z. So we're just going to keep it. X plus y minus z equals 8. This one is good. We've got y and z. Now, what you might say is, but this one didn't have a z. You're right, it didn't. So the better thing to do would be to write plus 0z equals 5. Go ahead and put that in there, but put a 0 with it. The same way here, we're going to insert a 0x plus 3y. So 0x plus 3y minus z equals 11. So now they all have an x, a y, and a z. Okay, so now we can write our matrix equation. Okay, so our coefficients are negative 2, 1, and 0. Then we have 1, 1, negative 1. And for the last one, we have 0, 3, negative 1. Okay, we need our variables. So that in order, they are x, y, and z. And that's equal to our constant matrix. So 5, 8, and 11. And you're done. You've written the system as a matrix equation. All right, for 6, we're going to write the equation and we're going to do some solving. Okay, so the following excuse me, is a predator-prey system where F sub 0 and R sub 0 are the number of foxes and rabbits in the current year. So the 0 is for like right now. Okay, and F sub 1 and R sub 1 are the number in the next year. So the number of foxes and rabbits in the next year. Okay, so we've got these 2 equations that we're going off of. So it says write the system as a matrix equation and use the matrix equation to predict the fox and rabbit populations next year if there are currently 50 foxes and 2,000 rabbits. All right, so first of all, we're going to write the system as a matrix equation. So notice our F sub zeros are lined up, our R sub zeros are lined up. So we're ready to pull out our coefficients. And these, I know they have a variable in them, so you're like, wait a minute, but these are the constants because it's what this equation is equal to. So we're going to put this in that constant matrix. Okay, so if we write our matrix equation, it is going to be the first constant, so 0.8 and a positive 0.02, negative 0.2, and 1.2. Okay, times, and you don't even have to put the times. I haven't written it the whole entire time we've been working. I don't know why I'm doing it now. Okay, times, and in order we have F sub 0, R sub 0. And that's going to equal our F sub 1 and our R sub 1. So my fox and rabbit population for next year. Okay, so if we know there are currently 50 foxes and 2,000 rabbits, that means that F sub O is 50 and R sub O is 2,000. So we're going to plug those numbers into the matrix where they belong. Okay, so we're going to have 0.08, -0.02, -0.2, and 1.2 times 50 and times 2,000. And that's going to equal, and we're actually going to solve those. Okay, so it's going to equal F sub 1 and R sub 1. All right. I was going to say something. I don't remember what it was. Good for me. I forgot. Oh, I know what I was going to do. So I was going to check this. So here we have a 2 by 2. That's what it was. And we're multiplying it by a 2 by 1. It's always good to check this. So yes, we can multiply, right, because these numbers match. And our answer here we know is going to be a 2 by 1. That's why I find this so helpful, is that I know, like, oh, okay, I'm going to have a 2 by 1 answer. Okay, so let's get going on this multiplication. In a 2 by 1, we're going to have 0.8 times 50 plus 0.02 times what? Good, 2,000. Okay, and then we're done with our first row. Second row, so negative 0.2 times what? Good, 50 plus 1.2 times what? Excellent, times 2,000. Okay, so there's the work for it. 0.8 times 50. 0.8 times 50 is, I don't know, I just have my final answer here. So let's see, 0.8 times 50 plus 0.02 times 2,000 is equal to, we're going to go with 80. And negative 0.2 times 50 plus 1.2 times 2,000 equals 2,390. Okay. So what does that mean? Well, that means, right, we said this is equal to that constant, F sub 1 and R sub 1. So we're going to have next year, F sub 1, there's going to be 80 foxes. And next year, R sub 1, for rabbits, there's going to be 2,390 rabbits. So we can interpret that. But just think how much work and time we're saving ourselves from solving the system with these kind of ugly decimals in it, because some of the systems are going to get more like that. All right, great work. I will see you guys tomorrow.